In this lesson, we're going to talk about vectors. A vector is a quantity that has both magnitude and direction. Our magnitude is going to be the length of the vector, and the direction will be determined by the way it's pointing. Some examples of vectors are force, velocity, and acceleration. So for example, the quantity 60 miles per hour is a regular number or scalar, has no direction. The quantity 60 miles per hour northwest is a vector because it has a size and a direction. So a vector is a directed line segment PQ with an initial point P and a terminal point Q. These are some important terms. A vector has a magnitude and a direction. It must have both to be a vector. The magnitude is the length of the vector and is denoted by PQ. It looks like very similar to little absolute value signs and an arrow over top. Two directed line segments with the same magnitude and direction are equivalent, regardless of where they are located. So as long as they are the same length and the same direction, they are equivalent regardless of where they start. The set of all directed line segments equivalent to the directed line segment PQ is the vector V equals PQ. So this is just some standard notation. Vectors are denoted in the book with bold lowercase letters, but for our purposes, in order to see them clearly, we're going to denote them with little half arrows over top of them. So we'll have an example as the vector U, the vector V, the vector W, etc. So what makes two vectors equal? Two vectors are equal if they have the same magnitude and direction. So if we let U be a vector represented by the directed line segment from R equals 7, negative 3 to S equals 4, negative 5, and V be a vector represented by the directed line segment from O equals 0, 0, and P equals negative 3, negative 2, we want to prove that they are the same vector. So we'll start by graphing the points. So R is 7, 3, 1, 2, 3, 4, 5, 6, 7, and then down 3. And it goes to 4, negative 5. So this is its initial point. The initial point is R, and its terminal point is S. And we want to prove that it's the same as the segment from O, which is at the origin, to P, which is negative 3, negative 2. So its initial point is the origin, and its terminal point is negative 3, negative 2. So to prove that they're equal, we must prove they have the same magnitude and the same direction. So let's look at magnitude first. So magnitude of vector U is going to be, we're going to denote U as RS. And to find the magnitude, you're going to take the square root of 7 minus 4 squared plus negative 3 minus negative 5 squared. Now magnitude is our distance formula. Okay, so I just plugged in my points into the distance formula, and I'm going to get a magnitude of the square root of 13. So now if I do the same for V, which is the vector OP, get the square root of 0 minus negative 3 squared plus 0 minus negative 2 squared. And that equals the square root of 13. So magnitude is the same. And then direction is slope. So this is my magnitude, and I want to know my direction. So my direction of u is going to be my slope of u. It's -5 minus -3, so my change in y's over my change in x, which is 2/3. And then my slope of v, which also equals 2/3. So they have the same direction and the same magnitude. Therefore, u equals v. Okay? So, simple enough. What I want you to try is make sure you can do this on your own, finding the magnitude and the direction. So now we want to know how else are vectors represented. So they can be represented in standard position, where the initial point of the vector is at the origin. So here, this vector, OP, is in standard position. If the initial point of your vector is at x1, y1, and the terminal point is at x2, y2, then the component form is vector v is x2 minus x1, y2 minus y1. It's all you're doing is taking the terminal point minus the initial point. The vector v1, v2 is called the position vector of the point v1, v2. So the position vector is the line going from the origin to that point. So let's look at some examples. So my first example is find the component form and the magnitude of the vector v equals pq, where p is -2, 2, and q is -2, 5. So I'll go over to -2, 2. That's going to be p. And then q is -2, 5. So I want to find component form and the magnitude. So we're going to find component form first. This is going to make our calculations for magnitude much, much simpler. So to find the component of v, you're going to do your initial point minus your final oops, that's a 5. So that's going to give us 0, 3. Okay, so now we can find the magnitude. It's going to be a lot easier because you're just taking the square root of 0 squared plus 3 squared, which equals the square root of 9. So the magnitude of our vector is 3. Okay, so the reason that you can just do this, you're doing this puts it at the origin, so the component puts it at the origin. It's essentially taking this vector and moving it down. So we're going from 0, 0 up to 3, 0, 3. So that's why you have this here. So 0 minus 0 plus 3 minus 0. So what I want you to do is try example. So now let's look at another example. So we want to look at some vector operations. So vector operations, we have addition and subtraction as our first one. So for addition and subtraction, you have vector u plus or minus vector v equals u1, u2 plus v1, v2, or you can put them together, vu1 plus or minus v1, u2 plus or minus v2. So these are coming from the vectors, and you take its pieces and you can add and subtract them. So in our first problem, we have uv. We let u equal -1, 3 and v equal 4, 7. So first, let's plot that. So we go -1 and then up 3. So that's u. And then we want v is 4, 7. So 1, 2, 3. Four, 7 is up here. And basically what we want to draw a parallelogram. So we take this point, and we're going to take this vector and kind of move it over. So we're going to go from here, we can draw our parallelogram. And move it to this point up here. So our vector, our new vector, or our sum of vectors is going to be up here. And that point up there is going to be 10, or 3, 10. So it went over 3, up 10. So basically you could take this vector, you say it went over 1, 2, 3, and it went up 7. So you count from here, over 1, 2, 3, and up, or over 4 and up 7. And that'll give you that parallelogram shape. We can also solve it algebraically using this formula above. So we'll have u plus v equals -1 plus 4, 3 plus 7, and we'll be left with 3, 10. So you can see the algebraic form is much simpler, so you might want to use the formula over the graph, but basically it's the sum and the direction, the magnitude plus the direction added together to get that parallelogram shape. So I want you to try u minus v to get on your own, and you should be able to get to the answer -5, -4. Alright? So let's look at some scalar operations. So the product of a scalar k and the vector u is k times u, which is the same as k times u1, u2, which is the same as k u1, k u2. So it can distribute to its components, its parts. So let's let u equal -1, 3. So let's look at 3 times u. So we'll have 3 times u is -1, 3. And using this property here, we can say that's -3, 9. And so that is our vector. So I want you to try this one and see what you can come up with. So now our scalar operations can be used in force. So you'll see in physics and some other applications that force is a vector and it's equal to mass times acceleration. So mass is the scalar and acceleration is the vector, making force a vector. So we have some special vectors. We have the 0 vector, which is 0, 0. It has no magnitude, and no distance, or no direction. The unit vector has a length of 1, and the vector u equals vector v over the magnitude of vector v is a unit vector in the direction of v. So we're going to take a practice problem of this. So we have an example. If v is -3, 2, verify that this here is the unit vector in the direction of v. So first we're going to find the magnitude of v. And again, just like the distance form, the magnitude is the same as the component form, each of the pieces squared. That's going to be the square root of 13. And now we have that u from before. U is going to be our vector v over the magnitude of v. So u equals v, which is -3 over our vector so it's just the vector v over its magnitude is going to give us u. So now we want to find the magnitude of u, because we want to show that it is a unit vector in the direction of v. So now we have the magnitude of u equals the square root of these pieces squared. So it's going to give us the square root of 9 plus 13 plus 4 over 13. 9 plus 4 is 13, so we have the square root of 1 equals 1. So the magnitude of this vector is indeed a unit vector. Okay? And lastly, standard unit vectors. So any vector can be written in terms of I and j. So I is always 1, 0, and j is always 0, 1. So if I want to take the vector, say our vector is AB, I can rewrite this using our rules of addition, and it becomes A0, B0. If I add these together, I get back to AB. Then I can factor out my scalar. So I have A times 1, 0, B times 0, 1. Then I can replace the 1, 0 and the 0, 1 with I and j. I'll get AI, BJ. So that's how you're going to see a lot of our unit vectors. You may also see them written. So I is equal to I hat, j is equal to j hat. So you may see them written different ways. And that is it for this lesson.